So LC history, the instrumentation, common detector. Okay, what's the big deal? Probably the most widely used analytical tool on the planet, I would argue, is the HPLC. And there's a lot of things it can do, right, for that very reason. You can almost ask, well, heck, why have both? Right? Why have both? Anybody have an idea? Kevin, have an idea? You think one manufacturer would put the other manufacturer out of business? HPLCs for liquids. You can do pretty much everything with it, right? Gas chromatography has to be a gas. Good. I think the argument would be, if you haven't done, I don't know, the folks who have really done research with this or played with this instrument would really have a feel for it. If there's a class, instrumental analysis, after you have that class, if you take it, you find out, you get your favorite instrument, right? And the GC is just so much cleaner, easier to use. And there's no moving parts. It's just, and the results are so sharp because they're gases. You have really sharp peaks. It's so easy to resolve peaks. If you have any mixture and you're going to put it in the HPLC, it's a liquid, and since things don't resolve so well, you only have, your column is only this long instead of it being 60 meters long. It's a lot more work to do the chromatography and get your peaks to separate. So to me, I think you wouldn't really need a GC, but you need a lot of time then, energy and effort, if you're just going to live with the HPLC. But okay. So I'm sure I'm going to murder this guy's name. I call it Sweat, since I don't know how else to pronounce this. All right. So folks like Sweat, Galileo, Newton, you name them. These guys are freaking geniuses. I don't know. I can't even relate to how they think, because the history is really interesting. This guy, you go back in time and he sees the trees all changing colors, right, and fall, and so those colors he thinks they got to be in the leaves. So what does he do? What he does is they have some access to chemicals like ether and things, so he jams a lot of these leaves into ether and he extracts out this, the black looking kind of liquid, and then he fills a tube with ground chalk, calcium carbonate, and then he just pours the stuff up on top, and he gets the colors to actually start appearing, all the different chlorophylls. He actually starts separating them out. So Sweat used sodium carbonate or chalk, and he actually separated out all the little chlorophylls. So Sweat's use of sodium carbonate is a very, what type of compound, Destiny, would you argue? These chromatographers, they like to use the word organic. Is this very organic or very inorganic? Or here we're using polar, nonpolar, or organic. What would sodium carbonate be? What sodium carbonate is, sorry, not sodium, calcium carbonate is chalk, right? What am I doing here? What type of compound is calcium carbonate? Covalent? Is it molecular or is it a crystal? Is it ionic? It's ionic. Calcium ions, carbonate anions. You can't get any more polar than ionic compounds. So this is to the extreme polar. All right. So since then, whenever this type of stationary phase is used, a polar stationary phase, they're going to refer to this as, Mariella, what would you guess? No. Try again. Normal. They call it normal. Since that's what was normally done, I guess, is just historically speaking. Okay. So when you have a polar stationary phase, normal chromatography. Later, around the 60s, liquid chromatographs came out. So sweat setup is kind of up here, a little rough schematic, right? What could be done to this type of setup to turn it into an HPLC? I think you got to realize what HP part stands for, because the LC is liquid chromatography, but what's HP? High performance, not cells, but it would make more sense to call it high pressure, right? So what could you do up here? You could, I don't know, put some big hunk of rubber up here and have some dude with a tube, and I can't draw a little bike pump, right? But a little guy just pumping the bike up and down, all right? Getting some pressure in there or something, or put a balloon up there or something to increase the pressure up on top. But then you need some way to add access to keep adding mobile phase somehow, so it wouldn't be very, you'd have to build the thing somehow. But that's one thing you could play with. Of all known organic compounds, only what percent can be analyzed on the GC? I think we mentioned this, Jamie. Did we mention this? What percent? Just guess. Now remember, GC is kind of restrictive. Well, GC, what's the question? Oh, analyze on the GC. And the GC is restrictive, Jamie, because it has to be able to volatilize it, because you can only analyze gases. And when you volatilize it, it can't fall apart and decompose on you like a sugar. So would it be the majority or the minority of compounds? Minority. It's like 20, yeah, somewhere around there. 20, 15, I don't know. I read 20, so I write 20. But any of those numbers sound good to me. LC manufacturers, like the guys, we just bought an instrument upstairs. They spend a lot of resources to make their liquid chromatographs ultra low volume in order to minimize, what's the bad thing with chromatography? Really what peaks? Really broad, right? So, yeah, no one's going to buy that. They're going to buy this, right? They want sharp, fat. So what is that called? You're not supposed to say broad peaks. What causes peak? Eddy or longitudinal. Those are two types of diffusion. They're called what broadening? It's for the Z. Starts with Z. Zone. Zone broadening. But you're right. It's eddy and longitudinal broad diffusion. But in general, zone broadening is what it's supposed to be called. That's the diffusion altogether. What is the difference between isocratic and gradient elution? So the whole idea of elution is this. This is elution. All right, let's get our samples to evolve and come out of the end of the column. That's elution. We're continually adding mobile phase up there. Our analytes elute is the terminology. Okay, well, what is an isocratic versus a gradient elution? If I just keep dumping mobile phase up here, I don't change any conditions whatsoever. Like, because you could change, just think of all the conditions you could change. You could, after 2 minutes, I'm going to wrap a heating blanket around there and heat it up. After 3 minutes, I'm going to start increasing the pressure when I crank up the flow rate. You just change it after all these different amounts of time, you can do different things. You change the mobile phase composition, right? Instead of dumping pure mobile phase, pure ether or ethanol, I'm going to mix 50% methanol and 50% ethanol, right? You can change, you can do whatever you want. So when you start changing things during a run, that's gradient. When everything stays the same, that's isocratic. So isocratic don't touch any buttons, right? You push start and just let it do its thing. You're not changing the mobile phase, you're not changing the flow rate, you're not changing temperature, you're not changing anything. All the exact same parameters. Gradient, change one or more thing during your elution, and that's a gradient run. Okay. So this is where they think of chromatography as a verb. Chromatography it really is a verb. I mean, to do chromatography, you're separating out your components. You're trying to resolve them, get pure components to come out the end of your column. In LC, there's something really easy to change to do chromatography. In GC, there's something really easy to change and to do chromatography. What would you do? What would you change in LC chromatography? Can you imagine something, Victoria, that would be easy to change in a liquid chromatograph, this type of thing. You keep dumping mobile phase up there. Something that would be kind of easy to change and have a pretty dramatic effect on what's going on. Pressure, except it's not going to have, there's something that's going to have an even more dramatic effect than pressure. You're right, pressure could really do something. Temperature too, yeah, but it's this whole column you got heat up, right? So it's for LC. Time, well, that'd be kind of like mobile phase. All these things are going to work. Mobile phase composition. But flow rate, all that stuff works. All I'm saying is mobile phase composition is numero uno. It has the most effect. It's the most dramatic, and it's going to be the quickest and the easiest. So that's LC. Mobile phase composition. But all those things you're yelling out work. But this is numero uno for LC. For GC, now you got a picture that, I don't know if you drew it on the quiz or not, but you got a picture of your big oven with a big fan inside. You got a 60 or 30 meter column going on in there. You're injecting your stuff. Hopefully it's all a gas. It has to be a gas, otherwise you can't do it in the first place. What could you mess with in GC to make a gradient elution? Easiest thing to change. It's going to have the most dramatic effect. All these work. Pressure, flow rate, but the biggest one was temperature. Temperature is going to be the biggest, have the largest and most dramatic effect. Okay, temperature. Because what you're controlling there is the distribution between the stationary phase and the partition is what you're messing with temperature. A flow diagram for our liquid chromatograph. I don't know if you know, but we just bought one upstairs. I swear, how much was it? It's like 40 or 45,000, somewhere around there, right? So, and why are they so expensive? Because they're really working to reduce this zone broadening. It's an expensive piece of equipment. But all LCs, HPLCs, they all have the same general configuration. And you're going to start out with a bunch of solvents, right? Here's your mobile phase. You have different solvents, A, B, C, D. In this case, you have 4 of them. And each solvent goes into this little contraption. Okay, because what you want to do is you want, I don't know, maybe 25% A, 75% D. So you could physically go and make this solution and put it in one of these containers, but why? It'd be a lot easier just to have the instrument do it. So the instrument can make up whatever mobile phase composition you want from these 4, what's in these 4 bottles. So this first contraption there is called the solvent proportioning valve. Proportioning valve. So whatever percent composition you want in your mobile phase, it'll set it. And you can change it over time, whatever you want to do. Okay. Well, then all that stuff gets sucked up there. It goes to the pump. And just imagine this pump. Realize you want results that look like this, right? Nice and sharp. You don't want results that look, because think of how else would you pump? I mean, it has to go forward and then come back. Forward, so it's pushing, then it's not. Pushing, then it's not. So you're going to have like these jagged things. You don't want that, right? So these things they're well built, and they're timed in the sequence where there's not just one valve. There's going to be more than one. Try to keep. They can't reduce all these pressure pulses all together, but they do the best they can. And so they usually have this pulse dampener. Ours doesn't have it. And you can tell if you really zoom up on the data. You can actually see the little pressure ripples. Okay. So I guess if we would have spent $50K, but who wants to zoom up that much anyway? So you get the pulse dampener. You will get rid of all those ripples. Okay. Well, you have to have some place to inject your sample. So now is the time to inject. Injector. Now there we did go full out, and we got an auto sampler, so you don't have to just push a button, the whole thing does everything on its own. You didn't have to inject. So you inject your sample. Since everything is going through, it's almost like a great big filter. You have to filter everything you inject in there. All these solvents, they all have to be filtered before you can put them into the HPLC. Anything you're going to inject into the HPLC needs to be filtered. So if you're going to do soda or water or whatever, blood, alcohol, whatever you're going to analyze, you almost have to run it through a filter first. Yeah, but right there can cause problems because what you're interested in might just be ending up there instead of where you're analyzing. So it becomes a project. So you inject it. Okay, so you have to do the separation somewhere, and you do it in the column. But these guys are roughly $600–700 a piece. And I'm told, I haven't done this, but this is a wrecked one. I'm told that if you just wrecked it, you jam it, because now it's uneven packing. Or if you tear the thing open to see what's inside and dig around, you wreck it. Right? They're pretty easy to wreck, I guess. This one's already wrecked, so you can tear it apart and look at it. But so what they have is these expensive ones are called the analytical column. So they're going to put something before it. The analytical column. So it's packed with all these different types of materials, whatever you're going to pack it with. And remember, this is where your eddy diffusion is going to be happening, so you want nice and even packing, really small particles, all that's going on. But to protect it, they put like a little $20 guard column in front of it. Guard column. So that's what's in this. That's what's in here. They're like $20. They clog up. Then you just change it out. But all that white stuff is a stationary phase. Someone just shook it really hard and broke it, and all the white stuff is coming out. Okay. So we go through your guard column, your analytical column. So now by this time, everything is separated out. You have pure components, if you did your chromatography right, coming out at the end of your column. They're all eluting, so you're ready for your detector. Okay. And then everything goes to the computer. Right? Everything's pretty much controlled by this computer. Okay. Oh, and the injector, too. It has to know when the sample was injected. So my dashed lines are kind of little electrical connections or something like that. And then everything ends up going to waste. But it doesn't have to. Like we have a project out there where they're not so sure why scorpions fluoresce. I think it's just a biological aspect of it. But anyway, we isolated that compound. So we sat there and we scraped the shells, got the little filings, extracted all the different compounds in there, did the HPLC. We got a bunch of peaks. We figured out which one fluoresced. So we did that just by collecting all the little peaks. Have a little test tube down there. The next peak's coming off. Change test tubes. Next peak's coming off. Change test tubes. And see which one fluoresced. So then we isolated the compound that does the fluorescing. A common LC detector, the DAD, D-A-D, Diode Array Detector. It's kind of an easy idea. But in order to really understand, I think you need to talk about absorbance. But just realize, I think it's easy enough to understand that if you absorb the color red, well then you have incident red light coming in, light's being transmitted through. There'll be less red light being transmitted through because you absorb some of it. That's the idea. So with a diode array detector, okay, what they're going to do is these have become really cheap. All these are just those little gratings, holographic gratings, but they're extremely efficient. So they have a light source, right? And then they put their grating on there like this, and then this is just fixed in space. It's just, so your little sample cuvette, right? All that light's passing through the sample cuvette. So then if there's anything that absorbs red in there, well, some of the little red will go down. But the point is the diode array, where does that come in? So it passes through the sample cuvette area. Then as that light's passing through, you have those little, well, I don't know if you guys do. You have all those big honking calculators. But the smaller ones, okay, the solar cells. So if I could get this right, you can see how the red is kind of here, the green's kind of here, the yellow's way out there. So if this was fixed in space, right, red intensity would always be here, green there, yellow there. So when nothing's passing through, zero it out. It's monitoring the intensity that's reaching each of those diodes all at the same time. So it's really nice. We have a UV-Vis spectrophotometer that requires you to sit there at each wavelength. It goes really slow. This guy, you get an absorbance spectrum all at once, simultaneously, all wavelengths at the same time. So it's really fast. So you can get what they call three-dimensional data. That's what this looks like. But that's kind of the idea. It's kind of illustrated in here. Okay. So there's our sample. So again, that's at the end of the column. Your pure analytes are passing through there. Partition chromatography. The most common type of liquid chromatography performed today is they call it bonded phase chromatography. So partition, you're being partitioned between two phases here. In this type of chromatography, the stationary phase is chemically bonded. So again, you have to have some stationary phase, and you'd think it's these little balls. No. What they're going to do, they're really good at making glass beads. By looking at this picture, you wouldn't think they're so good at it because they don't look all that uniform. But I guess manufacturing-wise, I guess that is extremely uniform. I guess when you electron microscopes, we're talking about, what, angstroms here. So these are glass beads, but they're coated with your stationary phase. So glass beads are the particle, okay? And glass is just silicon-oxygen bonds, right? Oh, I forgot my silicon. Right? So what they're going to do is they're going to chemically bond. And you can actually, this was a research project I was interested in doing. I think they have this now where, well, let's finish this picture first here. Remember we said like a C18 column, I think, last time? So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I shouldn't have picked something smaller. Right? So again, so you remember this is a silicon oxygen, so you have silicon silicon is all in here, right? I guess you should have. So the point is they try to coat that entire particle with their stationary phase. And you could put in all the H's, right? At the end you'd have an H3, all these other guys would be CH2s. But they can't coat them all. They do their best, but they can't coat the entire particle. It has some hydroxyls there, okay? Oh, I drew it too early. Well, we can change the patented process. We need to go the other way. All right? I guess you could have OH. Okay. So patented process is the other way. I screwed that up. Okay. So they don't let you know how they do it, but if you look in the patents, you can figure it out. And what I wanted to do is, they might sell this now, but I don't know I think they do. You go in, yes, they do. The last hotel I was at, they had this. There's this little section in the nice motels. At the ACS, we go to nice hotels, by the way. There's this. I remember this. You take nice long hot showers because it's all free. You get all the soaps and stuff, right? So you walk out, and then there's this little section of the mirror that's clear. So they coated it with an organic layer. This stuff. It's just this one little section. So, I mean, you can scratch it, you can rub it, doesn't matter. You can't get that stuff off because it's actually part of the glass in that one little area. And that's essentially this. So That's just going to be an oily film, though. You can wash that off. It'll come off. This stuff won't come off. This is part of the glass. On your above final sketch of a bonded phase, circle the region that can lead to peak tailing. Okay, peak tailing. So you're selling. Remember, you're selling this stuff at about $800 a pop. So again, you want there to be pretty peaks, but you don't want this to be happening. And it's really hard to stop. It's really hard to stop that from happening. And the tailing is all coming from that one little area that they didn't coat. Okay. So those hydroxyls that they didn't coat, that results in peak tailing. And again, why is this bad? Because, right, you want really sharp peaks so that you can resolve things. If you have tailing, things are going to overlap. It's going to be hard to quantitate, hard to identify. How about this one? Which phase would be referred to as reversed phase? It would be, yeah, nonpolar, because the other one was normal phase. All right. There's some general ideas how you can wreck the LC. Okay. Benzene is injected onto a C18 column. Then using the same separation parameters, it's injected onto a C8 column. Sketch how these chromatograms may look. So it's just benzene, so it's one peak, so let's put it right here. Okay. If I inject it onto a C8 column, is it going to shift? Now again, the C8, C18, that's this stuff, right? It's your stationary phase. This was a C18 example. Well, the tailing shouldn't be affected if they do their covering right. So they make the glass beads, assuming they did it really well, high quality, both stationary phases. So they won't have any hydroxyls there. But for LC, it's all about like dissolves like. What type of compound is benzene? Aromatic, carbon-rich, all carbons, however you want to think of it. The chromatography speak, very organic, right? I like the chromatography speak because it just seems more logical. Which column is more organic, C18 or C8? C18. So benzene should be more retained or less retained in a C18 column? More retained. So if you move over to a C8 column, how would you sketch it? What would you guess?
To the right.
It would come out to the this way or that way?
To the right.
To the right is this way, right? Right is over here. You're saying that it's going to be retained even longer then. Yeah, it's going to go the other way. All right? Right, it'll be the other way. So it's retained less. Okay. How could either of these peaks be made to elute faster? You don't want to go through the work of changing columns. Just do what? You could crank up your flow rate even more. That would work. But these guys, they can only withstand so much anyway, and maybe you're already at the max. It would be easier on your machine. Make the mobile phase composition more organic, right? Make the mobile phase composition more organic. If you had, let's say this was 40% water, 60% ethanol. What would more organic be? So if you're going to answer this question. Yeah, so make it 70% ethanol. Exactly, that's the thinking. And 30% water. Or like Christina said, just crank up the flow rate. But sometimes you're at the maximum anyway. So, okay. Using a C18 column, a sample of gasoline was injected onto a liquid chromatograph using a mobile phase of 45% ethanol, 55% water, column temperature of 30 degrees Celsius. Can this chromatogram be improved? If so, how? You kind of saw this earlier.
Increase the temperature of 5.
Okay.
For the pressure or
Okay. Something at 5.
yeah, at 5 you want to increase the organic.
Increase the organic because you're doing HPLC. So temperature, I don't know, I won't really do a whole lot. And plus it takes forever to heat up this thing. You can't really do much gradients on this. It's a big hunk of metal. All right, so I'd say, yeah, I got 5 minutes, make it, I don't know, 50% ethanol or something. Just increase it. Because you're doing reverse phase chromatography, you're doing, C18 column. Very, very organic column. It's what most common type of thing that's going on here. Okay. So why don't you take a few minutes and write GC, LC, or both next to each description below. Right? If it fits, you're thinking of GC, of gas chromatography or liquid chromatography, or both types of chromatography, next to each parameter here. I guess we could have neither too, right? GC, LC, both, or neither. And then I'll ask you and see what we can come up with a consensus. Shelby, was this yours? Yeah. Mm-hmm. Yeah. Yeah, there's some in there. You else want one? There's one left. Hmm? Mm-hmm. Oh, we've got 23. Hey, probably have 23 people here. So everyone can answer one. Right? Should we just get started? So let's start in the back for once. Sochi, you have number 1. What do you think? GC. LC, there's no way, man. You're not heating up anything. Right? Okay, keep going. Number 2. Mariella. I'd say, yeah, but why not? Why not both? Right? It's hard for you to know that, but just imagine computers. Heck, they can do whatever you want. Sorry, I'm supposed to write both. But it will be a much easier. I think it'll be a lot easier on the LC because we just got a new one. Our software on the GC is not that new, but the LC will handle it all. 3. This one, actually, the answer isn't both. One is actually better than the other one. A lot better. It's GC, and I think it's because of that 60 meter to 30 meter column. And they're gases, too. I mean, it's a lot easier to resolve. 4. Now here, GC has a mobile phase that moves through the stationary phase. Everybody agree, GC? LC doesn't? Yeah, they both do. How about separates mixtures into pure components? LC? They both. Stationary columns can be reused. So their columns can be reused. We're at Brad, I guess. GC. We can reuse this too for HPLC. Right? Yeah, it'll be both. Rapid results. I think you talk to the manufacturer guys and they're going to say both, right? I would argue GC, but probably both, I guess, right?
So both is the correct answer?
I don't know. That's relative. We're just trying to get a feel for this. But I think GC would be... But I've seen long GC runs too, so... Upon injection, Jamie, sample is immediately heated above the boiling point. GC, because you got to get it to vaporize. Extremely reproducible results. Don't make those HPLC guys mad, though. Right? It has to be both. Otherwise, they wouldn't sell them. Difficult to detect co-eluding peaks. Peaks that come out at the same time. Would that be possible on GC and LC? You have two things that come out at the same time. If you would think everything is different, so everything should come out at a different time. But realize that's only if you do your chromatography right. What if you don't do your chromatography right and the end of the column is right here? Everything coming out at the same time. At least red and blue are, right? So if you don't do your chromatography right, you're going to have co-eluding peaks, and it's going to be difficult to do anything. Detect, say what they are, quantitate, qualitate. That's got to be both. High cost of equipment. Shelby. LC's 40. That GC was actually 70 because he has an MS detector on him. And that was like 15 years ago. It's both. It doesn't take it takes into account university discounts. Uses capillary columns. Javier. Uses capillary columns. Yeah, only GC. Operation can be complex, requiring training. This is where the job security comes in. Matt.
I'd say GC more because it's automated, so probably you can say both.
Yeah, I'm going to say both. Actually, I think it's that HPLC just... I hate that thing. I'm getting to like it better, though.
That lady was pretty secure in her job.
Yeah. Only for... What was it? Only for molecular weight analytes that are less than 1,000 grams per mole. Only for molecular weight analytes. You can use this technique or techniques only for molecular weight analytes less than 1,000 grams per mole. All right. Now remember, GC it has to vaporize. LC you don't care. LC can do anything. GC, just think of something huge, right? You've got all these intermolecular forces, and just the bigger it gets, the tougher it can be to vaporize. So GC is, in general, anything bigger. I mean, 1,000 is awfully large. I don't see GC even doing this. But LC can do below and above. GC, there's no way it can do above. And that 1,000, I think, is still kind of high. So this is GC. Right? Only that fits GC pretty well. And like I said, I think that number 1,000 is pretty high for that. Oh, Albert, column is at a temperature that is less than the boiling points of the analytes. The column is at a temperature that is less than the boiling points of the analytes. They both, so GC has that capillary column, that orange polyimide capillary, and LC uses these guys. He says LC. Everybody agree? I had to prove this to a professor. I had to say, what are you talking about? You can do GC at below the boiling point. Why? Because everything has a vapor pressure. So you can operate and do gas chromatography. You just have to get it once it's vaporized, right? In the injection port, you vaporize it, but then the whole oven and everything can actually be operating lower than the boiling point of those components because they have a vapor pressure. They'll stay in the vapor phase.
It doesn't gum up your column?
No. In fact, it has advantages. So that one is both. You definitely want it for the HPLC because the things would blow up, right? You'd generate all this pressure in here, and you wouldn't want the pressure, the boiling point to be above the boiling point. I don't know. We're at Andrew. Typically, different analytes interact differently with the stationary phase. Agree? Both? Because the stationary phase is an LC as this packing like fatty C18 or something. The capillary column in a GC has this really same material, except it's in the liquid layer in the capillary column. And that's the whole idea, isn't it? That your different analytes will adsorb or dissolve, have different solubilities in their stationary phase, different affinities, whatever the word you like. So both fits really good for that, because that's chromatography. Typically, different analytes interact differently with the mobile phase. She says both. Do you agree? What is your mobile phase in GC? It's just like hydrogen gas or helium gas. Hydrogen if you're in pretty much anywhere now. So it's just, in GC, the mobile phase just pushes stuff through. But in liquid phase, in LC, dang, that stuff actually has to dissolve into the mobile phase to get moved along. So all your analytes have to somewhat dissolve in your mobile phase. But they could interact differently. Okay? So I would say LC. Because in the GC, it's just hydrogen gas. There's not much really going on there, right? Routinely analyze large molecules like proteins. LC. Eric. GC. Everybody agree?
Yes.
Mobile phase composition. Alyssa. LC. Commonly used high pressures. LC. Oh, you don't have to use the instrument to know this. The LC is typically around 400 to 500 psi. The GC, you read the little pressure, you can open it, you hear a little psh. It's maybe like 5 or 6 psi. There's hardly anything. So this is LC, most definitely. Commonly uses packed columns. Zach. LC, yeah, they're all packed columns. Look at that guy. Can have a mass spectral detector. We haven't talked about that yet. Both. And that is a relatively recent development. But, alrighty, so have a good, pick up your stuff. Have a good day.